Okay, we're now ready to deal with the transformations, that is the shifting of the parent or baby functions. These are on pages 15 and 16. The parent and baby functions are listed on page 14 of the Chapter 1 notes. I've made several videos for Algebra 2 explaining these in absolute detail. I will attach these videos if you choose to watch them. Your Algebra 2 teachers normally would have taught all of this, but I'm not sure if this particular year your classes got to it or not. Okay, so first off, I want to talk about shifting of what they now call the parent, when I was in school was called the baby, off the origin to HK. So we have these functions that we're supposed to know: linear, which is your oblique line, the absolute value; your quadratic function, which is the square function in the parabola that we beat to death during first quarter; the square root function, the cube root function, the reciprocal function, which is called the hyperbola; and the greatest integer function. Here are the parent functions. Again, you see these in your notes. What you don't see in your notes is this intermediate shift step. I go straight to the final answer. Now, what happens when you want to shift is we need to remember that everything that we are dealing with in math is we're doing distances. That's why I did a big deal of a distance. How do you find a distance? You subtract. Now, in these cases, we are going to be looking for directed distances, so I don't put an absolute value around it. The sign is okay because you can go down, you can go left, you can go right, so that's fine. So when I'm at 0, 0, my h and k are really 0, 0. So this is what it would really look like. Y minus k, x minus h. All those guys are zeros, and so I'm y minus x. But now what happens if they're not zeros? This is what it looks like officially. But so we can have it in function form, that is where we can find the value of y immediately. What do? We always do the additive inverse of the negative k, and it becomes a positive k. And this is why people get so daggone confused, because when I ask you what is, let's say, for example, the center or a vertex or the shift, people say, well, shouldn't I keep both of them or change both of them? If you were here, you say, what makes it 0k? What makes it 0h? So you can see this is perfect to where we're going to say what makes them 0. When we rewrite it, we have to realize that I've already done the additive inverse. So for k, I always keep what I see, the positive or the negative. But to find h, I need to do the opposite. So when I do the absolute value, this is what it technically looks like: y minus k and the absolute value of x minus h. When that's 0, 0, notice you have the baby. But I'm always going to do the additive inverse. So I can see take his opposite, keep. When I'm y equals x squared, again, if I showed you in the original form, this is what it really looks like. H and k are zeros, so you get the y equals x squared. Putting it in evaluating form, calculator form, function form, where this could be an f of x, g of x, h of x, r of x, I see that I need his opposite, and I keep him. And this goes on for all of the functions. For your square root function, you can see this is what it looks like. Your cube function, your cube root function, your reciprocal function. Always where the x is, you subtract the h, no matter where the crazy location is. And when I put it in the form that they tell you to memorize or learn, notice it's always got the plus k. Again, remember we're dealing with directed distances, and for calculator usage or evaluating usage, we always want it in what we call function form, which is y equals f of x equals g of x equals. Remember, since all these functions depend on distance from the point HK to the origin 0, 0, we see these subtractions up there. Now, knowing this helps us to find the shift, which I've already discussed over there, because we've always taught you to say what makes inside going to be 0, that is inside the parentheses or inside the radical. We're always asking that crazy question and it's driving you nuts, or in case of the hyperbola, what makes the denominator 0? But then we take the constant that's added outside no matter what it is. And as a reminder, this is x minus h. Notice what makes it 0 is a positive h, a positive k. But remember, with the k's, we've already taken the minus k and added it to the other side. So this is why the rule is as it is. So there's some examples now where I'm going to shift from 0, 0, aka the parent baby. And so I want to know what the shift is. So technically what I'm doing every time here is saying x minus h, set it equal, and I find h. Or what did I notice? I just said, oh, I want your opposite. And k is what you see is what you get. How do I interpret it h? It's telling me right or left. Positive means 3 right. How do I determine a k? It tells me up or down. And so a negative 5 tells me 5 down. So the shift is 3, negative 5. That's your translation. The function f of x squared has been shifted 3 right and 5 down from the origin of 0, 0 right there, which was our vertex. Now let's look at an absolute value function. Notice I show you, technically you're saying x minus h equals x plus 6. My h is negative 6. Notice it's always the opposite. K is what you see. A negative 6 means 6 left. A positive 7 means 7 up. So when I ask for the translation or shift, it's negative 6, 7. So the function g of x equals absolute x has been shifted 6 left and 7 up from the origin. Now, given the shift in translation of a parent or baby function, we can write the function. So suppose I give you y equals square root x, and I want to shift left and 5 down. Well, how do I shift left and 5 down? Notice this is our basic form. And so I know h is negative 3, so negative h is positive 3. K is negative 5, so your plus k is negative 5. Walla walla bing bang, I'm done. Y equals x cubed. And I want to shift right 7 and up 5. So I want to have this be 6. I don't know why I said 5. And this 6. So negative h is negative 7. So inserting in the formula, notice whatever h was, I want the opposite. Whatever k is, I end up keeping it. Giving a greatest integer. This is what it should look like. I want it to shift left 4. So that means, well, I don't know. We're going to change that to 7. Since I wrote 7, not 4. And so we want to shift this one left 7. Well, what does left mean? Left means negative 7. So h is negative 7. So negative h is positive 7. Or a left 7 is negative 7. So this has to be a positive 7. K is 0. You can write plus 0 if you want, but we usually don't. What about the oblique line? I want to shift down 8. So I don't want to change the x coordinate, but I want to go down 8. So all I have is my h is 0. Yes, I can write that in there, but why would you? Now we want to analyze a graph and determine how it should look generally without having to graph. So using the transformations of a square root function to get this idea across. It can either be graphed up and right, down and right. That's usually what most of you have done if you've not had me. But it can also go up and left and down and left. These are the only possible shapes. Now, examining the square root function in its most complex form, it could have a constant multiplier, some number in front of the square root, and the x could have a coefficient. So I'm going to call A the constant multiplier, and the B will represent the coefficient. The coefficient of x determines whether you're going to open right or left. If the coefficient of x is positive, you open right. If the coefficient of x is negative, you open left. So notice the coefficient of x was positive, the coefficient of x was positive, the coefficient of x was negative, the coefficient of x was negative. Now, the constant multiplier on the square root symbol, like A on x squared of the parabola, determines whether you open up or down. If it's positive, you open up. If it's negative, you open down. So since this one opened up, K was positive. The A was positive. Since this opens down, the constant multiplier was negative. Up, constant multiplier positive. Down, constant multiplier negative. So now let's look at a couple of cases. Let's look at what would be up and right. So I've put things in. What's the coefficient of x? It's positive 2. Positive means right. What is the constant multiplier? It's 5, which is positive, which means up. So my graph is going to go up and right. It's going to take on this shape, and the shift is 2, 3. So I now know generically it looks like 2, 3, and it's going to go up. What's going to happen is the 5 and the 2 are going to determine some other qualities to where what are the y coordinates exactly going to be. That's not our interest. We just want to know the shape. And so now continuing in this vein, let me put up, another board. I didn't feel like going into the other room. Case 2 is down and right. Notice the coefficient of x is 2, which is positive, so it's right. The constant multiplier is negative, so it's going to open down. And so this says I'm going to move right and down. So that would be the shape. Notice for all of these, no matter what I'm going to do, I'm going to have them all have a shift of 2, 3 to show you that I could give you the same graph, and that's why you just can't look and say, this is what goes. Now, this part, 3 and 4, are new to many of you if you did not have me as a teacher. I need to go up and left. What's the coefficient of x? Oh, wow, it's negative. And since it's negative, it's going to open left. What is the constant multiplier? It's 5. It's positive. It opens up. So this graph is going to go up and left. Notice I still have the shift as 2, 3. And my final example, down and left. The coefficient of x is negative, so it opens left. The constant multiplier is negative 5. It's negative and it opens down. And so I'm going to go left and down. And notice when I did my shift, it's still going to be 2, 3. So this is analyzing before you ever plug a graph into your calculator. Before you ever do anything, you want to have an idea of what's going on, and this is called analysis. And this is what makes math become easy when you get these patterns and you get this thinking into your head. Math becomes beautiful because math is just a series of patterns. That's all it is. Patterns over and over. That's why it's called beautiful.